So now that we have learned about important kernels, um, like very popular ones, let's talk about the kernel trick and see how things are going to work with the kernels. What are the functions that we can use as kernels that can basically represent the similarity of our data points in the new feature space? So the thing is that for a kernel to be able to work, we said that we do not want to have access to phi. So we have x to phi of x, right? So from vector x to phi of x, that's the kind of transformation that we are going to do. But instead of working with phi of x, we don't have access to it. What we have access to is the kernel function that is defined between our data points, and it can be represented as a function of our data points in the original input space, but it means that it is a similarity between our data points in the new feature space. So basically, what we are saying is that there should be a way such that we can calculate this kernel without accessing to phi of x and phi of y, right? So, so that instead of mapping our data to this feature space, we should be able to work with the kernel matrix that is defined based on the data points. And because we are working with this kernel matrix or a similarity matrix, the method that we can apply, it should be able to work based on the similarity between the data points only. Because as we said, we don't have access to phi of x. So if our method needs to have access to phi of x, it cannot be used in this kernel method. So in other words, we can say that our data mining method that we are going to use should be able to be kernelized so that we can represent it, we can show it in a way that it can work with the similarity between data points instead of the data points themselves. So how are we going to do that? That is done by kernel trick. So the first thing is that we should show whatever tool that we are going to use can work only based on the similarities or the dot products. So we should show that our method can only work with this kind of dot product between the data points. Then if we can show that, then all we need is just to have access to this kernel matrix. Because instead of the dot products, what we are working with is the kernel matrix that are going to be calculated according to the original feature space. So we won't need to have access to phi of x directly, right? So then we are going to be done and we are going to have a kernel trick that works. So for example, we have talked about the Gaussian kernel and we said that the feature space for the Gaussian kernel has infinite dimensionality and we really cannot write phi of x that much. But then if we have a method that doesn't need to have access to phi of x directly, but can only work with k, the kernel matrix between all the data points, then we are going to be okay. And that method is actually going to work in this feature space, not the original input space, and without accessing to phi. That is infinite dimensional. Okay, so what kind of functions are going to give us those kinds of kernels? So we have seen the very popular ones. We have seen the linear identity kernel, we have seen the polynomial kernel, we have seen the RBF kernel. But are these the only kernel functions? No. So we can have many different kernel functions that are represented by kernel matrices. So again, kernel matrices are the n by n matrices that are defined based on each pair of our data points, and they represent the dot product between our data points in the new feature space. So as long as we have a kernel matrix that has some specific features or characteristics, then we can use that as our kernel, and we don't need anything else. Now, what are those characteristics? First of all, our kernel should be positive semi-definite. You remember positive semi-definite from when we were doing SVD and PCA, right? So we had a positive semi-definite matrix. K is positive semi-definite if and only if for any vector A, we can write A transpose KA, and we get to a number that is either positive or zero, so non-negative number. So K is an n by n matrix for any n by 1 matrix A. So this is n by 1, this is 1 by n. We are going to get a scalar, a 1 by 1 number basically, that is going to be non-negative. If for all the n by 1 A's, we have this situation for K, then our K is positive semi-definite. Kernel matrices must be positive semi-definite. Also, they should be symmetric, right? A part of being positive semi-definite is that it should be symmetric. In other words, the K, the dot product of phi of x and phi of y should be equal, right? Phi of x transpose dot phi of y, we know that it's equal to phi of y transpose phi of x. So our kernel matrix also should be symmetric. So the kernel between xi and xj, or between x and y, should be equal to the kernel between y and x. All right. So if our kernel matrix is positive semi-definite, then we can say that we can use it as our kernel matrix that we can define all different methods on top of that. So basically the kernel properties is that our kernel matrix is n by n, defined over all pairs of our data. It's symmetric and it's positive semi-definite. Positive semi-definite also means that the matrix, the kernel matrix, has real non-negative eigenvalues, right? So that's what we need for our kernel matrix. Now, we also said that, all right, if we want to do the kernel trick, we need to be able to define all the operations in our method that we want to apply the kernel trick on to be defined according to the dot product between the data points, or in other words, to be defined only based on the kernel matrix. Let's see how we can do that. Let's see some basic kernel operations and how we can use those kinds of operations and show how we can use the kernel matrix in them. So let's start with very basic operations. One of the very simple operations that we used to do on a numeric vector in the input space was that we could calculate the norm of a data point or the norm of a vector, right? So what was the norm of a point? It was basically, it was equal to x transpose x, right? Now, we have to show that we can calculate, we want to show that we can calculate the norm of a point in the new feature space only using kernels without having access to phi of x. So we have had x, we now transformed it into phi of x. What would be the norm of our new data points? The norm of our new data point represented in the new feature space is like this. It's the norm of phi of x, right? Okay, from the definition of norm above, we know that the norm of phi of x is equal to phi of x transpose phi of x. Well, from the definition of kernel, we know that this is equal to the kernel between x and x, right? So we don't have access to phi of x directly. We don't have access to these, but we can calculate the norm of the data point in our new feature space only based on the kernel, right? So basically the value of norm is square root of this, square root of phi of x, which is square root of k, x, and x, right? So this is the norm, actually. So it's the square root of x transpose x, which is that. So basically, the norm of all of our data points can be calculated only based on the kernel. So that was the first operation that we had. Now, let's look at another operation. Suppose that we want to find the distance between our data points. So if I want to calculate the distance between two data points in the original input space, like for example, if I want to calculate the distance between xi and xj, I can do this, right? I can calculate it according to xi minus xj L2 norm, right, for Venus law. So now that I transform my x to this new feature space phi of x, if I had access to phi of x, I could calculate this distance like this. It would have been phi of xi minus phi of xj squared, right? Now, let's see if we can rewrite this in terms of our kernel matrix and see if we can just use the kernel matrix to calculate this distance, right? So what is the value of this? This is equal to phi of xi minus phi of xj transpose phi of xi minus phi of xj. Okay, if we do this dot product, we will get to phi of xi transpose phi of xi plus phi of xj transpose phi of xj minus 2 phi of xi transpose phi of xj. Why? Because phi of xi transpose is equal to phi of xj transpose, right? So we are going to have two of these. Okay, all right. We know that phi of xi transpose phi of xj is actually the kernel between xi, the first one, phi of xi transpose phi of xi is the kernel between xi and xi. Plus the second term, phi of xj transpose phi of xj is kernel between xj and xj. And then the third one, phi of xi transpose phi of xj. So we have two kernel between xi and xj. Okay. So we do not have access to phi of x to be able to calculate this, but we can calculate this distance only according to the kernel matrix values. Now that I have this, then the actual distance is the square root of this, right? So the square root of this whole thing, so the square root of the distance would be the square root of phi of xi minus phi of xj norm, which is equal to square root of k xi plus k xj minus 2k xi and xj. So that will give me the distance between the two data points. Okay, so that sounds good. So we can calculate the norm of a data point and the distance between two data points using the kernel matrix without having access, direct access to phi of x. Now, if we look at this, we can actually see that the k between xi, xj, so you can, according to this equation, that we can calculate the distance between xi and xj, phi of xi and phi of xj, we can see that the kernel between xi and xj is actually equal to 1/2 of norm of xi squared, norm of phi of xi squared, norm of phi of xj squared, minus the distance between phi of xi and phi of xj squared. In other words, we can conclude that the more this distance between phi of xi and phi of xj is, the less the kernel value between them is. So the less the similarity between them is, right? So that's why we, although the kernel is equal to the dot product between phi of xi and phi of xj, we also see the kernel as a kind of similarity between phi of xi and phi of xj. Okay. So now let's look at another operation that we use a lot in data mining, and that is calculating the mean of our data points. So we said from the beginning that if we want to have a 1-point representation of our data, mean is the best 1-point representation, right? Best 0-dimensional representation of our data to minimize the sum of squared errors. Although it has its own issues, like for example, being not being robust. But let's see what mean in our feature space is. So suppose that I had x and I just transformed it into phi of x, and I want to calculate the mean of my new data points in the new feature space. The sample mean in the original space, we calculated like this. We said that it's equal to 1/n. N was the number of data points. Summation over all of our data points. So I equals to 1 to n, and then xi's, which were our data points. Now, in this new feature space, our mean is going to be similar. So we are going to have, let's call it mu of phi. And the calculation of sample mean in the new feature space is going to be 1/n sigma I equals to 1 to n. Instead of xi, now we have phi of xi, right? So let's see if we can calculate this mean of our new data points in the new feature space according to the kernel matrix only. I'm looking at this, and whatever I try, I see that in any ways that we want to calculate the mean, we still need to have access to phi of xi. There's no other way that I can rewrite this that we don't need the phi of xi, and we can write it as a dot product between two xi and xj's, or phi of xi and phi of xj's. So it seems that if I don't have access to phi of x, I will not be able to calculate the mean of my data in the new feature space. That sounds very disappointing, right? So we really cannot calculate the mean vector itself in the new feature space. That's sad. But let's see if we can calculate something else. You remember when we calculated the covariance and variance and all of that, we needed the mean, right? But we could rewrite the covariance and variance in a way that we only need the norm of our mean data point. So basically, what we can think of is to calculate the norm of this mean vector in the new feature space and see if we can actually calculate that. Let's see. So if I want to calculate this new thing, which is the norm of my mean data point, I can rewrite this like that. This is actually equal to our mean transpose mean, right? Okay. We have already written the formula for mean itself. So it's equal to 1 over n summation I equals to 1 to n phi of xi transpose multiplied by 1 over n summation of I equals to 1 to n phi of xi. Right? Let me actually call this guy j and this one j so that we don't confuse the two. Okay. So if I multiply these two with each other, what do I get? First of all, I get 1 over n squared for 1 over n here, 1 over n there. And then I will get sigma I equals to 1 to n, j equals to 1 to n, phi of xi transpose dot phi of xj. Oh, wow, nice. So from here, this is familiar to us, right? This is actually equal to the kernel between xi and xj. So I'm getting to something that is familiar to me. So this will be equal to 1 over n sigma I equals to 1 to n, j equals to 1 to n, k xi xj. Oh, that's very nice. So we can calculate the square of magnitude of our mean, right? So we can calculate this according to the kernel matrix only. What is it? Let's look at it. We are going over all the I and all the j, and we are summing over the kernel values between all xi's and all xj's. So if I'm looking at my kernel matrix, it's as if I'm going over every element in the kernel matrix and I'm summing over that. And then I'm dividing that by 1 over n squared, right? So we have n squared elements in the kernel matrix, right? So basically this whole thing is the average of the K matrix. So average of every value that is in my kernel matrix is going to give me the magnitude of my mean squared in the new feature space. Okay. Now, we said that for calculating the variance, we can rewrite this to only meet the norm of mean. Let's see what is the variance in the new feature space. Can we calculate that according to the kernel matrix? Okay, let's try that. So you remember the variance, right? What was the variance? The variance was 1 over n sum over all of our data points and their norm squared between themselves and the mean of our data. That was the sample variance. Now that we have the new feature space, the variance of our data in the feature space, so let's call sigma squared of phi, it is equal to the sample variance, or total variance is 1 over n, I equals to 1 to n. Instead of xi's, now we have phi of xi's, right? Minus, and instead of our original mean, now we have the mean in the feature space squared. Okay. If I don't have my phi of x, I don't have my phi of xi. Also, we know that we cannot have mu of phi without having phi of x. We have already seen that here, right? But let's see if I can figure this out, maybe make it a little bit different and fix this so that we can calculate this. Oh, oops. Okay. All right. Okay, let's open this up and see what is this thing that is inside the sigma. If I look at inside the sigma, phi of xi minus mu of phi squared. What is this? This is equal to phi of xi minus mu phi transpose dot phi of xi minus mu phi. Okay. What is this? Let's open this up. It's equal to phi of xi transpose phi of xi plus mu phi transpose mu phi minus 2 phi of xi transpose mu phi. Okay, I'm getting closer and closer, right? So this first thing, well, it's very familiar. It's obvious, right? It's the kernel between xi and xi. The second term, well, that is also familiar. It's actually the square of magnitude of mu phi, right? Which we have calculated above, right? Which is equal to 1 over n squared sum I equals to 1 to n, j equals to 1 to n, k xi xj. Okay. And now let's look at this other one. Let's open this one up. So far, we have this is equal to k xi and xi plus 1 over n squared sigma I 1 to n j 1 to n k of xi xj, now minus 2 phi of xi transpose, and instead of mu of phi, let's just write the formulation for average, sample average. 1 over n sigma, let's call it j, equals to 1 to n phi of xj, right? So I don't have access to phi, I don't have access to mu of phi, but let's see if I have access to this whole multiplication of these two. I can rewrite this. I can take n out, right? So I will have minus 2 over n. And then because I is invariant to this j in the sigma, I can just push this inside the sigma. So I can rewrite it as this. J equals to 1 to n phi of xi transpose, because it doesn't matter that j is changing. As long as I don't have I here in the sigma, phi of xi is kind of constant within the sigma, right? So I can just move it in, multiplied by phi of xj. Okay, nice. Now I have another familiar term here, right? This is the kernel between xi and xj. All right, so now I can say that this whole thing is equal to k between xi and xi, like what we have there, plus 1 over n squared, sigma sigma I equals to 1 to n, j equals to 1 to n, k of xi and xj, minus 2 over n, sum j equals to 1 to n, k of xi and xj. Okay, so without having phi of x, I could not calculate mu phi, I could not calculate phi of xi, but I could calculate the sample variance in my data according to the kernel matrix eventually. So I could calculate the variance only in terms of k. Oh, sorry. Basically, we are not there yet. Sorry, I forgot about that. So far we have calculated only this part, which is inside the variance. We're not done. Let's calculate the variance itself. So the variance itself was 1 over n sigma I equals to 1 to n, this thing that was inside that we calculated. So that is k of xi plus 1 over n squared sigma sigma I1 to n j1 to n k xi xj plus minus 2 over n sigma k xi and xj. Okay, yeah, this is the whole variance that we have in the data. Okay, so just to not to make a mistake and mix this I with this I, because they are two different things, what we can do is that I can call this one K to make things easier. So this is K, and this is also K. right? So if we rewrite this whole thing, so it's a sigma of this, it's going to be equal to 1 over n sigma k of xi and xi, I equals to 1 to n, plus 1 over n to the 3, because there is 1 n squared here, 1 over n here, summation of, we have 3 summation, I equals to 1 to n, j equals to 1 to n, k equals to 1 to n, k, the kernel between xi and xj, minus 2 over n squared, sum I equals to 1 to n, j equals to 1 to n, k of xi xj. All right. Now, because we don't have a k inside this here, so when we are multiplying, when we are summing this k n times, k equals to 1 to n, it's as if we can remove this and put an n here, right? So basically, it will be equal to 1 over n sum of k xi and xi plus 1 over n squared, because these will cancel, sigma I equals to 1 to n, j equals to 1 to n, k of xi and xj, minus 2 over n squared, I equals to 1 to n, j equals to 1 to n, k of xi and xj. Now, these two are basically the same thing. So it's going to be 1 over n sigma I equals to 1 to n k xi and xi minus 1 over n squared, because it's like this one minus the second one, the third one, right? Sigma I equals to 1 to n, j equals to 1 to n, kernel between xi and xj. Okay, now we are done. So now we have calculated this whole variance, this one, which is basically this one, only according to the kernel. Okay, let's see what this is. First of all, this thing looks familiar to us, isn't it? Let's go back and see where we have seen it. Let me go back. Oh, I have seen it here. What is it? This is the square of magnitude of my mean, right? So this is mu phi squared. And, well, here, what I'm doing is that I am summing over k of xi for all the i's. So basically, I'm summing over every element on the diagonal of my kernel matrix, and I'm dividing it by n. So it's as if I am taking the average of diagonal values of kernel matrix K. So this is another way to look at the variance of our data in the new feature space. It's going to be equal to the average of our diagonals on the kernel matrix minus the mean, magnitude of mean of our new data in the new feature space squared. Okay. All right. That sounds interesting. Another thing that we used to do a lot when we were dealing with our data was that we tried to center our data, right? We said, for example, for SVD, for PCA, we had this assumption that our data is centered. We calculated the Z first, right, in the PCA algorithm, for example. Let's see if we can do that in the feature space also. Okay. So because I don't have any space left here, I will move to this side. I hope you can zoom in later on and take a look at that. So let me write, actually, this is the mean. This is the variance. And here we are going to talk about centering the data. Okay. Let's see what that is. So when we did center our data in the original space, what we did was that we had x and we had mu also, and we calculated z as x minus mu for every data point that we had. So in the feature, if we do the transformation, it would be as if we are doing phi of x minus mu phi, right? For all the phi of x's that are out there. But we don't have access to phi of x. We don't have access to mu of phi either. So it's not possible directly. But let's see if we can calculate the kernel matrix that is centered instead of calculating the phi of z. So that was phi of z, right? So let's see if I can calculate the kernel, the centered kernel. I put a hat here to represent the centered kernel between xi, every pair xi and xj instead. Okay. Well, we know that originally the kernel between xi and xj is equal to phi of xi transpose phi of xj, right? Now, the centered kernel should be equal to phi of xi minus mu phi transpose phi of xj minus mu phi, right? So instead of just phi of xi and phi of xj, I replace it with phi of xi minus mu phi, which is centered phi of xi and centered phi of xj. Again, we don't have access to any of those individually, but let's see what is the multiplication of these two. So if we do that, we will see that it's equal to phi of xi transpose phi of xj minus phi of xi transpose mu phi plus mu phi minus mu phi of xi transpose plus mu phi. Okay. Well, we already have some familiar forces here. So this is k, xi, xj, right? First of all. And this is norm square of mu phi, which we have it from before, which is equal to 1 over n squared sigma sigma of I equals to 1 to n, j equals to 1 to n, the kernel between xi and xj, right? Again, what we can do for these two, is to rewrite mu phi as 1 over n sigma phi of xi y equals to 1 to n, right? Or j, doesn't matter. So if we actually do that and open everything and do the magic or algebra, we will get to this. So this will be equal to k of xi and xj. I recommend you to do it at home so that you can practice and learn. So it's going to be equal to k of xi and xj minus 1 over n sigma k equals to 1 to n. Let's call it L so that you don't make a mistake. The kernel between xi and xl plus 1 over n sigma L equal to 1 to n, the kernel between xj and xl minus 1 over n sigma L equals to 1 to n, another sigma m equals to 1 to n, the kernel between xl and xm. Okay, so although we cannot calculate the centered data points, each of the centered data points, but we can calculate the kernel between the centered data points, or in other words, we can calculate the centered kernel. So it will be equal to the original kernel entry minus these things that you can see here. So minus the kernel between the original xi and all other data points, and the average kernel between the original xj and all other data points, and then the average kernel that exists in between all the data points with each other. Oh, sorry, this is n squared, so this is the average. Okay. From now on, we assume that in all of our feature matrices, we have the centered. We work with the centered ones. So basically, we assume that our k is centered. And if it is not centered, we can just use this to center the k.